The modern electrical grid requires constant reconfiguration. Every day, grid operators must energize and de-energize massive high-voltage equipment, capacitors, transformers, and reactors, just to balance loads and route power. This process relies on massive mechanical circuit breakers. These heavy physical contacts slam shut to bridge the gap and allow thousands of volts to flow. In a standard operation, these mechanical breakers are entirely disconnected from the electrical rhythm of the grid. They operate at random times, making contact at completely unpredictable points along the alternating current sine wave. Because this timing lacks any intelligent control, statistical probability guarantees that sooner or later, a breaker will close at the exact worst possible microsecond. Hitting these critical points on the waveform triggers violent, mathematically predictable electrical transients that shock the entire local network. These transients manifest as extreme undervoltages, sudden overvoltage spikes, and massive inrush currents tearing through the lines. Every random switching event sends a physical and electrical shockwave through the substation, actively degrading multi-million-dollar infrastructure piece by piece. Consider a completely discharged capacitor bank. The moment it connects to a live power source, it behaves identically to a momentary short circuit. If a mechanical breaker happens to close the circuit exactly when the alternating source voltage is at its peak, the system experiences a violent equalization. The network tries to push current into the capacitor instantly. This generates a massive high-frequency inrush current that places extreme mechanical and thermal stress on both the capacitor bank and the breaker itself. Power transformers present a different physics problem. When a transformer is taken offline, magnetic energy is left behind, locked into its iron core as residual flux. If the transformer is re-energized randomly, the incoming electrical wave creates a new prospective magnetic flux that superimposes directly on top of that residual flux. This compound effect pushes the transformer core deep into magnetic saturation. To sustain this saturated state, the transformer draws a magnetizing inrush current that can reach up to 3 times its normal maximum rating. Both capacitive and magnetic grid components are subjected to severe wear, simply because the brute force physical connection ignores the timing of the electrical wave. Shunt reactors carry their own risks, particularly during the de-energization phase when the breaker contacts pull apart. Because inductive currents in reactors are relatively low, the insulating gas inside the breaker can extinguish the electrical arc prematurely, slightly before the alternating current naturally reaches zero. This is known as current shopping. When the current is suddenly severed, the magnetic energy stored inside the reactor's inductance has nowhere to go. It forcefully discharges into the surrounding stray capacitances of the windings and bushings. This sudden discharge creates a steep oscillating overvoltage. If this voltage spike exceeds the dielectric strength of the still opening breaker contacts, the arc reignites across the gap, bombarding the reactor insulation with high-frequency transients. Finally, long, uncompensated transmission lines pose a severe risk during reclosing operations when trapped electrical charge remains on the open line. Closing the breaker when there is a large difference between the supply voltage and that trapped line voltage injects a massive traveling wave. When this wave reaches the open far end of the line, it reflects backward, doubling in amplitude and creating a dangerous overvoltage. Whether the load is capacitive, magnetic, or inductive, ignoring the phase angle creates specific physical failure mechanics that degrade the grid. The solution to this wear and tear is a digital approach called point-on-wave, or controlled switching. The core mechanism relies on an intelligent electronic relay. This controller constantly monitors real-time voltage and current waveforms of the grid, mathematically calculating the exact optimal phase angle to connect or disconnect a specific load. When an operator initiates a switch, the controller intercepts the command. It artificially delays the physical trigger to the breaker, releasing it so that the contacts meet at the precise optimal microsecond. This chart shows voltage and current waveforms during random capacitor energization. Notice the intense vertical spikes occurring at connection. The peak inrush current surges to 4 times its nominal value, propagating dangerous transients everywhere. Look at this chart showing the exact same operation executed with a point-on-wave controller. The violent spikes are completely gone. By timing the connection as source voltage crosses zero, current establishes gradually, eliminating destructive inrush. The specific mathematical target depends on the hardware being switched. For Y-grounded capacitor banks, the optimal target is exactly 0 volts across the breaker contacts. For opening shunt reactors, the physics require a different approach. The controller times contact separation so that when the current naturally hits 0, the gap is wide enough to withstand recovery voltage without reigniting. Point-on-wave technology removes the need to brace for impact. It uses exact calculations to ensure the impact never happens. The algorithms governing this timing are exact, but they are bottlenecked by physical reality. The controller must execute its commands through heavy mechanical linkages that are inherently imperfect. As a circuit breaker begins to close, a mobile contact moves toward a fixed contact, shrinking the distance. This shrinking gap introduces a critical variable, known as the rate of decrease of dielectric strength, or RDDS. The physical distance between those contacts determines their ability to block electricity. As they move closer together, their approach velocity dictates the downward slope of that falling dielectric strength. If the rising grid voltage exceeds the remaining dielectric strength of that shrinking gap, the insulating medium breaks down. This intersection triggers a pre-arc, prematurely beginning conduction and ruining the controller's calculated microsecond timing. To prevent pre-arcing and ensure the software can do its job, the physical circuit breaker must possess exceptional mechanical repeatability. Its operating time from command to connection can only vary by plus or minus half a millisecond. Successful point-on-wave implementation requires marrying advanced predictive algorithms with ultra-precise mechanical hardware capable of consistently defeating the RDDS curve. Historically, managing these violent transients meant building bigger, heavier equipment. Operators relied on staggered mechanical drives and physical pre-insertion resistors to absorb the shock of connection. These physical workarounds are heavily compromised. They add immense mechanical complexity to the breaker, wear down over thousands of cycles, and introduce dangerous single points of failure into the grid. This device is a modern numerical relay controller. It replaces hundreds of pounds of copper and mechanical dampers. It processes all timing mitigation entirely in software, achieving clean connections without relying on sacrificial hardware. By stripping away brute force mechanical dampeners and replacing them with frictionless software, the overall reliability of the substation drastically improves. This creates a cascade of grid-wide benefits. The first is pure asset protection. Neutralizing steep voltage transients prevents long-term insulation breakdown in highly expensive transformers and shunt reactors. Second, it cuts maintenance requirements. Eliminating aggressive arcing and massive inrush currents prevents the steady erosion of the breaker contacts themselves. Third, it stabilizes power quality. The controller prevents the severe voltage dips, ground potential spikes, and harmonic disturbances that frequently cause secondary protection relays to misfire. Every time a breaker opens or closes, these software-driven calculations transform what used to be a violent mechanical necessity into a seamless, controlled event. By controlling the exact microsecond of connection, point-on-wave technology ensures the high-voltage grid operates efficiently, protects its infrastructure, and runs with absolute mathematical precision.